Okay, let's go ahead and take a look at section 28.3, which is average rates from curve graphs, and section 20b.1, which is instantaneous rates of change. Now, let's go back to our former example of the train, the Shinkansen, that left Tokyo at 12 o'clock and then traveled 200 kilometers in 1 hour to get to Nagoya. Okay, and here's the graph that we had from before. And notice that what we said is that the average speed for this one is going to be the change in the distance, which is the change in the distance here. This is the distance axis right here, divided by the change in the minutes, or the time, which is this axis here. And what we came out with was 10 kilometers for every 3 minutes. So that would be the average speed for this entire journey. Of course, being that the entire journey is going to be represented by a line. Now, also remember that we said that this represents also the slope. And so if we go ahead and just use this green piece of paper that I have here, notice that the slope doesn't change for any particular value that I have on this line. So the slope remains the same. Now, let's go ahead and, since we're dealing with slope, let's just go ahead and review a little bit about slope. And let's say, for example, that this piece of paper is joining any two coordinates. What is the slope here? Well, if the slope is that means that the slope is 0 because there is no change. But, say for example, if I go like this, then the slope that joins those 2 points would actually be a positive slope. And if I compare it to this one, this slope is actually bigger. Okay, a larger positive slope. Okay, and this one over here is going to be even smaller, but still positive. In the same respect, I can go negative as well. This is going to be a small negative slope, a larger negative slope, and even a larger negative slope. Okay, and so we need to also go ahead and connect that to rates of change. So this is a small positive rate of change. This is a larger rate of change. And this is an even larger positive rate of change. And I can do the same thing for the negatives as well. Now, what we're going to do is, let's take a look at this example again. One of the things that I'm hoping that you realize is that this is probably not an accurate representation of the Shinkansen at all. Of course, because what this is saying is that right from the get-go, bam, you're traveling at 10 kilometers per 3 minutes. If that happened, you'd be like this, and that doesn't happen. And neither does that happen when you actually come to a stop. You don't just all of a sudden just come to a stop. If that was the case, everybody would still be flying forward at 10 kilometers per 3 minutes. The more accurate situation is that, of course, when you get onto the Shinkansen, it slowly starts and then it picks up speed, hits its maximum speed, and then as it gets into Nagoya, it starts to slow down again. So if we were to go ahead and really try to depict a little bit better with what happens with the Shinkansen in terms of its distance with regards to time, it probably looks a little bit more like this. It starts off very slow, starts to pick up a little bit of speed, okay, and then after that it starts to slow down again because we're coming into Nagoya. And so I think this would be a little bit more of an accurate representation of what is actually happening with regards to the Shinkansen as it actually starts from Tokyo and goes all the way to Nagoya. Okay, so notice that what's happening now then is that I'm still going to want to talk about, say for example, the average rate of change, but I no longer have a line anymore. Basically what I have is a curved graph. Now, the whole thing about calculating slope, of course, if we wanted to calculate the slope, we still need 2 coordinates. So that means that we can still go ahead and calculate the slope or the average rate of change, but the thing is, it's not going to be the same for the entire trip. So as we said before, this, when it was a straight line, had a constant rate of change for the entire duration of the trip, which is probably not an accurate representation of the Shinkansen trip itself. But if I go ahead and I take a look at this, let's say for example, if I talk about this red line here, oh, now my average rates of change actually are a little bit different because of the fact that the Shinkansen is actually slowly gaining speed. It reaches its maximum speed, and as it comes into Nagoya, it starts to slow down again. But I can still go ahead and talk about the average rates of change, and I can still calculate them in exactly the same way. It's just that when I go to different respective intervals of time, that average rate of change is probably going to be different from other intervals and other rates of change within the trip. So let's just take, for example, if I was to, let's just use this paper here. If I was to just go from 0 to 10 minutes, then of course the two coordinates that I would be using is this right here and that right there. And if I was to go ahead and actually calculate the slope between those 2 points, notice that the average rate of change is actually positive, but less than what I had with the blue line. So of course that means that the train is actually starting to pick up speed, but at a slower rate of change. Now if I was to go to the next point over here, to this point, notice that what I have is I have this rate of change, okay, the slope that is connecting those 2 points, and that looks like it's a little bit more in line with what we had before if we used a straight line graph of 10 kilometers per 3 minutes. Now if I was to go ahead and use the next 2 points, then the next 2 points would be like this, and notice that what I have is I have an actual positive, a larger positive rate of change than this blue line, and that makes sense, right? Because after a while you start picking up speed and you're actually traveling more or less at your maximum speed at this point from 20 minutes on. And then from here, notice that we continue with that, still more positive rate of change than what our blue line graph would actually provide. But then it starts slowing down, right? Because this is a less positive rate of change, which means that it's probably closer to what we have with the straight line graph. And then after that, notice that what we have is we have something that's a very small positive rate of change, which in other words means that the train is slowing down, but still moving forward. So the moral of the story then is that we can still go ahead and calculate average speed, but that is probably going to be different for each interval that we have, because of the fact that we're no longer dealing with straight lines and we're dealing with curves. So we can still go ahead and do that. Now,